So on the test for independence, here's the main difference between a test for homogeneity and a test for independence. Now, they both are organized in a two-way table. That's what makes it sometimes difficult to understand which is which. So another common situation that leads us to a two-way table is when we have a single random sample. So we only have one sample of individuals. We choose them from one single population of interest. And then we classify them based on two different categorical variables. So it's one overall sample from a single population, but we're measuring two different variables on that one sample. So our question now becomes whether or not there's a relationship between the variables. So our test for independence occurs when we run into this specific scenario. So when we want a test that compares the relationship between two or more variables measured on one single group of subjects, we're running a chi-square test for independence. Now, how does this differ from a test of homogeneity? Because that's going to be the key, is being able to identify which one we run, because our hypotheses and our conclusions will be different based on which test we run. Okay, so with this one, we have one single group, but we have multiple variables in question. With the test for homogeneity, we had what? Almost the exact opposite, right? We had multiple groups, but we only had one single variable that we measured. So we had multiple groups, multiple samples that we worked with, and then we looked at the distribution of one variable for each of those groups. So when you read through the questions on these, especially when we get to Monday where we're mixing them all together, you have to try to decipher, do I have multiple groups in which I'm only measuring one single variable, or do I only have one single group, but I'm looking at two or more variables and how they relate? So that's the key, is being able to do that with these types of problems. Now, when we run a test for independence, essentially what we're looking for is whether there's an association between our variables. So we're trying to determine if the two variables are related somehow through some sort of association. So in essence, this is somewhat like when we were back in first semester and we talked about scatter plots. Scatter plots were a way for us to graph two quantitative variables and determine if there was some sort of relationship, correct? So if they had a linear relationship, whether it was positive or negative, we could say that there is an association between the variables. So as one increases, the other increases. Or as one increases, the other decreases. So things like that. The difference here is now we're working with categorical variables, but we're still looking for the same thing. Do they have some sort of relationship? Does one possibly affect the other? So we're looking to see whether they're independent or not independent. So with this test, when we want to test, or the hypotheses that we want to run, so the hypotheses that we're actually testing, the null is just like we would expect. We always assume no difference. So for this test of independence, we would assume no association. So they're not related to each other in any way. So the null, there is no association between the two categorical variables in the population of interest. So that second part in brackets is just your context that comes from your specific question. And then the alternative hypothesis is just the negation. There is some sort of association between the two categorical variables of interest. Your book likes the terms association, so no association versus association. You might see it written a little bit differently, so the book I used to teach out of used the term independent. So, one thing I want you to maybe add in, or at least be aware of, because based on what you're working with, like when you get to the AP exam, they might use the terms interchangeably. So what we're looking at here, if there is no association between the variables, what would we say about their independence? That they are independent, right? So another way that you might see this hypothesis written out is instead of there is no association, you might say that the two categorical variables are independent. Okay? So you would say whatever two variables you're measuring, this variable and this variable are independent of each other, which then means in our alternative, if there is an association, that would mean that they are not independent. So here you would say your two variables are not independent. So as far as homework goes, since we're using our book and the book prefers the term association, you would want to stick with the ones that are in the actual box there. So there is no association between, or there is an association between. But they also have another way of writing that using the term independent. And so it's almost the exact opposite. So two variables are independent versus not independent. No. No, and as far as like when you guys are working this out, like the only reason I would say stick with the association is because if you're using your book at all, it's always going to use that term, and so it'll make more sense. But if you like on a quiz or a test, if you use this version with independence and not independence, I'll still count that the same. So I will grade it the same. On the AP exam, they should take either version as long as you're using the correct terminology there. So we're okay with those? All right. Then the next thing would be our conditions. Once we have our hypotheses stated, we look to see what our conditions would be. So notice they're the exact same conditions as we had for goodness of fit. They're the exact same conditions that we had for the test of homogeneity. So random, either a random sample or a randomized experiment. 10%, our sample must be less than 10% of our population. Or if it's an experiment, we don't need it at all. And then the large counts, all expected counts, must be at least 5. And since our information will be put into a two-way table, just like the test for homogeneity, you can test the large counts condition with that same shortcut. Find the smallest row total, find the smallest column total, multiply them together, divide by the overall. That'll give you your lowest expected cell. Or, when we talk about how to do this in the calculator, you could actually run the test on the calculator and then check your matrix B. It'll have all of your expected counts listed out. You just make sure that they all are at least 5. So a couple different ways of doing it. Okay there? All right. So in the test, and don't write all this down because we've already written most of it down. Plus, this tells you how to do it all with the formula. We're going to probably do it more with the calculator, but it's important to understand the formula portion. Again, you might be running a test for independence, but they might say, calculate this specific expected value. So on that last slide, knowing how to find the expected value is important. On another point, they might say, here's the two-way table, find the specific component of the statistic. So you would actually have to take the specific cell, find its expected count, subtract, square it, divide by expected to get the actual component. So when they ask for that component of the chi-square statistic, they're asking you for one specific calculation on the cell. So we've already talked about, for the test of independence, we know the hypotheses. We did that last slide. We know the conditions were met, or we know what the conditions are because it's the same as we've been working with. So if we were doing it by hand, we would calculate our chi-square statistic. So that would be for each individual cell, taking the observed value minus the expected and squaring that difference, and then dividing by the expected. So that would get us one component. Each one of those individual pieces we calculate would be that component for that cell. We'd add all those components together, and we get our chi-square value. Once we have our chi-square value, we would use our chi-square CDF, plug in the chi-square value for our lower bound, 1e to the 99 for our upper bound, and then notice for degrees of freedom, we calculate it exactly the same as we did for homogeneity. So since our data is organized into a two-way table, we are going to calculate degrees of freedom in the exact same manner. So number of rows minus 1 times number of columns minus 1. And just like every other chi-square test, the p-value is always the area to the right. So that's why the lower bound is always the chi-square. The upper bound is always 1e to the 99. So we're always going to the right with our positive values. Okay with that? So then, as far as calculations are concerned, you run it exactly the same as your test for homogeneity. As far as the calculations are concerned, as far as doing it in your calculator is concerned, everything about the test for independence is identical to the test for homogeneity. So you would take your two-way table, put it into a matrix, go into your stat test list, find the chi-square test. So it's the exact same option even in the calculator. So you choose that chi-square test, run it, and you get all the same information. So when you're running these tests here, the reason it's so important to know which test you're running, they're calculated the exact same way. Homogeneity and independence, everything about it's identical. The only difference is what hypotheses you create. So the hypotheses are completely different, which then means your conclusions are completely different based on context.
So to figure out which one you should just like look at the last question of it.
Yeah, the best thing to do would be to look at that, because a lot of times they'll actually tell you, so they might say, look, is there an association? If you see the term association, that means you're running independence. So you had one single group of multiple variables that were being accounted for. Otherwise, for homogeneity, they might say, are the distributions the same, or are the choices the same, things like that. That's when you're looking at your test for homogeneity. So looking at how they word the question would be extremely important, yes. Otherwise, just examining the problem and knowing, do I have one group with multiple variables? There's my independence. Do I have multiple groups with one variable? There's my homogeneity. Does everyone understand that? All right. Now, some cautions. Because when we're talking about the test for independence, when we reject the null and we say that there is an association between the two variables. So remember, our null is that they're not related. There's no association between it. If we fail to reject, then that's just there is no association. But if we do reject, we say that there is some sort of relationship between the two variables in question. However, this test does not imply a causal relationship. So just because there is a relationship of some sort, it doesn't mean that one causes the other. Remember when we had that conversation last semester, we talked about shoe size and reading scores. In elementary schools, the larger the shoe the kid wore, the higher their reading score. Well, that doesn't mean if we buy larger shoes, we'll get better reading scores. There's lurking variables at play. Now, if it's an experiment, then yes, you could imply the causation. So if it's an experiment that you ended up rejecting the null for, an experiment does allow us to work towards that causation. So one does cause the other to change. Okay, so when you're running just a normal test of independence, now if it's not an experiment, if you're just running the normal test, it shows there's an association, but nothing can be said if one changes the other. The other thing you have to be careful with here, if you have extremely large samples, as part of the calculations within these tests, if we have extremely large samples that we're working with, what we're going to find is that with those large samples, we will always reject the null, even if there might not actually be evidence to support the fact that there is an association. And so that has to do with the background and the workings of the actual mechanics where the calculations are occurring. Those large samples will throw those results off. So you don't want samples that are extremely large, otherwise you're pretty much always going to reject the null regardless of whether you should or not. Now, the other thing to talk about, when you're checking your conditions, when you get to the large counts condition, all of your expected counts have to be larger, or at least 5. Now, with this test, and this test only, so this only works for the test for independence, when you look at the variables in question, if you run your large counts condition and one of your cells or multiple of your cells are less than 5, if it's not like all of them, so maybe like only 1 or 2 are lower, there is a possibility to fix that by looking at your categories. So you're going to have 2 different categorical variables. Now, if 2 or more of the categories can logically be combined. So the key is you can't just combine 2 categories for the sake of it. If you can logically combine 2 categories, if they're related enough that you're like, well, I can put those together and they mean about the same thing. If that's the case, then what you can do is take your two-way table and condense it down. So, for instance, if I have a two-way table, so I have 2 different variables. So let's say I have 3 categories for one, and I have 4 categories for the other. Now let's say that this cell right here has an expected count of 4. And that's the only one that has an issue. All the other expected counts are good to go. Well, if we look at this then, what we want to do is examine, well, maybe one of these categories here could be combined. Maybe they're not different enough. Like I could say, well, these 2 things are kind of the same thing. I can combine those 2 columns. Or you can look at your different rows. Maybe the rows fit together nicely. So for instance, let's say category 2 and 3 for the rows here logically work together. So those are ones I can logically put together and be fine with. Then what would end up happening is I would take these 2 rows and combine them into one overall row. I would put all of their counts together. So all of their observed counts get put back or get put together. So now I still have 3 columns, but now I only have 3 rows. So groups 2 and 3, or categories 2 and 3 here, get combined into one overall group. So what I have to do is I go back to my observed counts, and I combine them. So I remake my two-way table. Instead of a 4 by 3, I now have a 3 by 3, and this second category is actually 2 of them put together. Does everybody understand that? So now, if I go through my process and I calculate my expected counts, because I combined numbers together, I should have expected counts now that will be larger than 5. If I run my expected counts and I'm still not larger than 5, then you have to look, well, maybe I need to combine more, or at that point you'd be like, well, it's not going to work because that cell just doesn't get to 5. So that's something you have to kind of weigh at that point. But if you have a test for independence and your cell count is less than 5, you don't want to give up on it right away. You want to look to see, are there any categories I could logically combine together? And if so, combine them and then rerun it and see if that fixes the problem. And if it does, then you can produce the test based on that new information. Sound okay with that?
It would be pretty obvious when you're supposed to combine those.
Yeah, I mean, it's got to be something that, so, well, obviously it's going to be something where you found a cell that's less than 5. That's going to be your tell that I have to combine if I can. But as far as what to combine, it should be very obvious. If it's not obvious that they can combine together, then you're not going to combine. Like you wouldn't want it, like if I'm looking at colors here, I wouldn't want to combine like blue with green or blue with orange, right? So blue and orange are two completely different colors. I'm not going to combine those. But if it was something else where like 2 and 3 could logically be combined under one heading, then I could do that. So like I don't know my colors very well. Like purple and magenta, would those be pretty close? Okay. So if I had purple and magenta, we could be like, well, they're kind of the same thing. We could put them together and combine that way. So it should be something that, like, if you're going to combine, it should be something that anyone looking at it should be like, oh yeah, I agree, those two could combine and be the same thing. And then you do it and redo it, or rerun the test from there. Okay there? All right. That's it.